So on today's video, we're going to be covering an application problem. In this one, it's a problem regarding wet laundry. So the problem goes like this. So we have, clothes we're going to put our clothes our clothes in a dryer. And we basically want to find out how long it will take for the clothes to be 95% dry. And we're giving this by the following initial conditions. We know that at the beginning, when we put our clothes in the dryer, the humidity it's 100%, right? The clothes will be fully wet when we put them in the dryer before the cycle starts. Um, and then we're getting that after 5 minutes, the clothes basically are 50% wet or 50% dry, however you want to see it. So they're asking us how long would it take until the clothes are actually 95% dry. So how long it will take? You guys can take a guess. Whether it will take us maybe a few minutes, up to 30 minutes, maybe an hour. I'm thinking that maybe some of you have already used a dryer before at home, and you know how long the cycle usually takes. But let's use this problem, and you can see how we can apply differential equations to something that we use in our daily life, like just like washing clothes. So in this case, let's define our variables. So we have that y it's equal to the moisture content. So basically our whole equation will be in terms of moisture. So basically we're tracking the moisture content as a function of time, where y prime is the rate of moisture loss. So how fast are we losing that humidity? How fast are we losing that water? In this case, we have this variable. So initial conditions, we know that at the beginning, when time is 0, the amount of wetness is equal to 100% wet, or 100% moisture content. And then after 5 minutes, it's 50% of that. And we're using this equation to model this. So this equation is basically stating that the rate of loss of humidity or moisture is proportional to the moisture content. So meaning that the less moisture it is, or the more water there is, basically the faster it will dry. The less it is, there, and so on. So you guys can understand there. And once you solve this, you'll see this is basically an exponential equation. So let's solve this one. So we have this model ready. So this is the equation. So you guys know the first step to do will be to change that y prime into dy dx. And then this is equal to negative k y, where k is just a constant. So if we continue to solve, then we have over here dy over y, which is equals to negative k dx. So it seems that they are already, or I guess in this case, it's not dx, right? It will be actually dt, because we're doing this with respect to time. So it will be dy dt. All right, so with this, let's continue solving. So it seems that it is already separable. So we can actually integrate both sides. So we have the integral of dy over y, and this will be equal to the integral of negative k and dt. So solving both of them, we are going to get natural log of y, and this is equal to negative k times t plus c, right? Let's continue. So we raise both sides to the exponent, to the exponential. So you have e to the natural log of y equals to e to the negative kt plus c. We can rewrite this, and we know this is y equals to e to the negative kt times e to the c, which we can instead rewrite as y as a function of t is equals to capital C e to the negative kt. And then we call this our general solution. Right? This is the general solution that models this equation. So now we can apply our initial conditions to determine what is actually that particular solution that we need in order to find our time. So let's apply those initial conditions. So we do apply initial conditions, and we know that when time is 0, y will be equal to y naught. So doing this, we can apply that, and basically we get then y of 0 is equals to c e to the negative k times 0. And then we know that k times 0 is just 0, so we'll get then that um, y naught, right? Because that was y of 0 equals to y naught is equals to c e to the 0. We know e to the 0 is 1, so then we know here that y naught is equals to c times 1, in which we know that y naught is equals to c. Therefore, our particular solution for this case will be y of t is equals to y naught e to the negative k t. This is our particular solution. So that was the first initial condition. We still got one more unknown. We don't know what that k value is. So this is where we apply that second condition. So let's apply that second condition. So apply second condition. Right, for two unknowns, we need basically two equations. So this one we know that when y equals, well, time equals 5 minutes, y of 5 it's equal to let's say this will be equals to, what was it, 0.5 y naught. So let's apply that, and we get then y of 5 is equals to c e to a negative k times 5. And if we do this, or in this case, we're not gonna have any more c, this is y naught. So we can rewrite this, and this will be 0.5 y naught equals to y naught e to the negative k times 5. You can see what we have y naught in both sides, so we can cancel that. And we have here 0.5 is equals to e to the negative 5k. So basically we're solving for k, so in order to bring that k down, we take the natural log on both sides. So natural log of 0.5 is equals to natural log of e to the negative 5k. So it's natural log of 0.5 is equals to negative 5k. So in order to get k, it's equals to natural log of 0.5 over negative 5. And once we solve that, this is equal to 0.1386. So when we do this, then we can get that our actual value, our actual solution is the following. We have y as a function of time is equals to y naught e to the negative 0.1386 t. And this will be the equation that will model our like our moisture or water loss. This will be our actual particular solution, or more exact particular solution. So basically, if you see our graph or our function, it looks something like this. We have time on this axis and y, or basically the moisture loss on this other one. And our function that models this, if you see, it's a decaying exponential. So basically will be something like this. And you can see that as the time progresses, can be here. So the more when we start, we have more water, but as time progresses, you can see we have less water, so it becomes less deep. So the more time it passes, basically the less um, moisture we have, of course, because we are drying that um, we're drying our clothes. But you can see that the rate at which it happens is not linear. It's basically it's non-linear. It's exponential. So the less moisture content there is, actually the more it will take to for it to like dry out. So let's solve our problem. We have this, so let's find out then the time to actually do that. So this is our equation, and basically what we're gonna be doing now is solving for time. So from this equation, let's apply one more condition, solve for time, and we'll get that time that it takes to lose 95% of the moisture. So let's apply the condition. So let me write this then. To reach the 95% loss of moisture, we need to solve for T. So we have here then our equation, y of t, it's equal to y naught e to the negative 0.1386 t. And we want 95% loss of moisture. So this will be translated as 0.05 y naught, right? Because if you remember, y naught at the very beginning, that represented 100% wet, or in this case 0% dry. Why not? So if we have 95% loss of moisture, or basically 95% dry, it means we have 5% wet, which is what we're trying right here. So this is what we want. So let's apply those numbers and let's rearrange. So then we'll have here 0.05 y naught is equals to y naught e to the 0.1386 times t. We have that y naught on both sides, so it can cancel out. And then we have 0.05 is equals to e to the negative all of that times t. We take the natural log of both sides, and this will be negative 0.1386 times t. And then solving for t, we get that this will be the natural log of 0.05 over negative 0.1386. And when you do this, I hope that your predictions were correct. You guys can take a minute and solve this. You can put pause on the video before I give you the answer. But if you already did it, then that's fine. The answer is 21.6 minutes. That's the unit that we have been working since the very beginning. So basically, then we have that the time needed to reach 95% moisture loss is 22 minutes. So 22 minutes to lose 95% of water, humidity, or moisture content. And this is our answer. So you can see we can apply differential equations in many things like everyday activities, just like even drying our clothes. So next time that you wash your clothes, you can try this yourself, do an experiment. This can be easily done. You can just you can basically wait your clothes, your wet clothes, before you dry them, and then maybe get them to weight them again after 5 minutes. Compare the weight difference. That's how much water you lost, basically, and then you can do this and find out if it actually will take that time. So next time that you have to set up the whole dryer for like about an hour or so, you can even set it for less, knowing that about 20 minutes in, you maybe are done and you can save yourself some money, some time, and energy in your home. So that's it for this video. We'll see you in the next one. And as always, good luck.